Everyone, Mr. Neighbor here. Today we're talking about Chapter 15, Waves. First, we're going to look at 15.1, which is different types of waves. But before we do that, what is a wave? So a wave is a disturbance that carries energy through matter or space. It doesn't carry the matter, but as the energy moves through, it moves or shifts the matter. It doesn't carry the matter with it, though. It's only energy moving through matter. So what are some different types of waves? We have mechanical waves and electromagnetic waves. This is two of a bunch we're going to talk about. So first, mechanical waves. Mechanical waves are any wave that requires a medium to flow through. It requires matter to be present. For example, waves on a pond, earthquakes, sound. It's a mechanical wave because you need air to vibrate. In space, there is no sound because there is no air. The waves can't travel through anything. So those are mechanical waves. They need matter to flow through. Electromagnetic waves, they are any wave that does not require a medium to flow through. So radio waves, television waves, light, those are all examples that don't need a medium. So within those categories, you have different types of wave movement. So waves move in different patterns. The first pattern we're going to talk about is transverse waves. That's when a wave particle moves perpendicular to the wave. Remember, perpendicular is at a right angle. So example, when a crowd does the wave, that is an example of a transverse wave. Electromagnetic waves are also transverse waves, which is light. Longitudinal waves are compressed waves. That's where you have sound waves building on each other. They're particles that move parallel to the direction of the wave. So you'll see kind of these lines building up on each other because in those areas, the wave is being compressed. You can do this with a slinky very easily and see that longitudinal wave kind of flow through it. You can make a transverse wave out of a slinky too. So those are two of the common ones we use a lot. Surface waves, those are more talked about when we have waves in the ocean or earthquakes. They are when particles move both parallel and perpendicular to the direction of the wave, creating an elliptical motion at the boundary between two different mediums. So if this is your water and this is your air, the boundary between, you have this elliptical type motion. Same thing when we have an earthquake. This is what the ground does, and this is what the air is doing, or the ground and then the ocean above it. So different types of waves have different patterns to them. Surface waves are a combination of both. So let's look at the transverse wave a little bit more closely. So we had this image before, but there's different parts to transverse waves. There's the crest, which is the highest point in the wave, the trough, which is the lowest point in the wave. You have the amplitude. The amplitude is half the distance from crest to trough. So it's like draw a line down the center of it, from that center line to the top, or the center line to the trough. That would be the amplitude. And wavelength is the distance from crest to crest until the wave begins to repeat, or other equivalent parts of the wave. It's very, very easy to look at from crest to crest, though. So the wavelength here would be right there to right there. That would be the wavelength. Another way to highlight the wavelength, I might go from this point here, where it goes up and then down and then up, and then it would start over there again. I also could go from the trough here to my other trough where it would be repeated. So those are all the wavelength. Next, we have the longitudinal or compression waves. The longitudinal wave has the compression part. The compression part is where you see the buildup happen, where things are bunched together, these areas right here. That would be the compression part. The refraction is where the particles are farthest apart. So this right here would would be the refraction part. In this area, it would be the spaces in between the blue, where the particles seem less dense. It still has an amplitude. That amplitude is right here. And the wavelength is the distance from compression to compression. So where's the wavelength line? So right here to where that refraction happens again, which is right there. And you see the orange line right there. That is all the wavelength right there. So it's still the horizontal measurement for that. So those are longitudinal waves. And I want to talk about seismic waves. These are pretty much the waves that we talk about with earthquakes. So they are a combination of longitudinal, transverse waves, and then surface waves. Okay, so we're going to talk about P waves, S waves, L waves, and R waves. First of the seismic waves, the P wave, P standing for primary. They are the very first wave that happens after an earthquake occurs. They are the fastest moving, and they travel through solids and liquids. They are a compression wave, so you see the compression happening right here. And then that compression is furthering along until it's all the way over here. So it's traveling through the earth. It's also known as push-pull waves or longitudinal waves. Next, we have the S wave. That is the secondary wave. S meaning secondary. They are slower. They follow right behind the P wave. They cannot travel through liquid. So we're going to see a diagram in a bit about Earth and where P waves travel through the Earth, and where S waves will travel and where they can't travel. They cannot travel through liquid, so just remember that. And they are transverse waves. Remember, transverse waves are the ones like the wave you would do in a crowd. So you see the upward movement. Damage is not typically done by P waves or S waves during an earthquake. That's because the structure holding up buildings that is in the ground, that's being shifted with buildings. In the next couple slides, you'll see different waves where that structure is not going to be shifted the same way as the surfaces, and that's where the problems occur in earthquakes. All right, so here we have a diagram of Earth and underneath Earth's surface. Here we have the Earth's crust. Here we have the liquid outer core and the solid inner core. The epicenter is where the earthquake actually happened. From that comes P and S waves. P waves in yellow, S waves in that purplish black color. So notice that in this region right here, there are no S waves, no purple. These are only P waves. Notice what the waves have to go through. A liquid core. S waves can't go through liquid. They just don't make it through. Hence why you see all these primary P waves making it through, but not any S waves. So you will see the activity of earthquakes lessen because the S wave isn't making it through. There's other reasons too, but you're seeing that happen right here because of the liquid core. The other wave we're going to see, there's one of them that doesn't go through liquid either, which is good, so it doesn't travel all the way through the earth. The last seismic waves we're going to talk about are L waves, which are love waves, and R waves, which are Rayleigh waves. So they are the last waves to come. Rayleigh waves come behind S waves, and then, love waves come behind S waves, and Rayleigh waves come behind those. So P waves are the fastest, S waves are second fastest, love waves are next, and Rayleigh waves are after that. They're a combination of primary and secondary waves. So a combination of the transverse wave and the longitudinal wave. That combination makes them especially bad. If you look right here, a love wave, it kind of has this churning motion where part of the earth is shifted left and the other part is shifted right. And you can kind of see this overhang that it has, an indentation. When buildings that have structures going straight into the ground like this are pushed sideways,